Hello friends, welcome to CEC Live Lectures. Dear friends, today in this session we are going to talk on wave motion. This is an introductory lecture where we are going to discuss on wave motion, and for the discussion on the topic we have with us in our studios Dr. Sonia Bansal. Dr. Sonia Bansal is an assistant professor and she is teaching in YMCA University of Science and Technology. Friends, if you wish to ask questions from Dr. Sonia Bansal on today's topic, then do call us through our toll-free number. Our number is 1800110430. I repeat, our number is 1800110430. Now, I would like to welcome our guest, Dr. Sonia Bansal, and would request her to explain us in detail about the wave motion. Hello, ma'am. Welcome to the lecture.
Thank you, Geetika. Dear students, today we will discuss about the wave motion. We discuss about the basic introduction about the wave motion, how we get the waves, what are the amplitude, what are the frequency, what are the time dependent, and at last we discuss about the wave equation. Now we start with the wave motion. First we discuss about the what are mechanical waves. In this lecture we discuss only about the mechanical waves. The mechanical waves where we discuss about the sound waves, water waves, and the waves transmitted in a guitar string. These are the mechanical waves, and in the elastic medium are needed for the travel of the mechanical wave. If we talk about the mechanical wave, then we require the elastic medium of the mechanical wave. The mechanical waves can appear when an initial disturbance is made to the medium. On this microscopy level, if we talk about the mechanical waves, is the forces between the atoms in a medium are responsible for the propagation of the waves. Means if we talk about the wave, then we will discuss about the propagation of the waves. And in the microscopy level, the forces between the atoms in the medium are responsible for the propagation of the wave, means movement of the waves. The particle of a medium do not experience any net displacement in the direction of the wave as the wave passes. It means the particle is moving, and this moving particle in a medium do not experience any type of displacement in the direction of the wave as the wave passes away. The particles simply move back and forth through the distances about their equilibrium position that creates a wave. Means we are getting a waves after the movement of the particle. What is the wave? Wave is a process of propagating oscillation in a space. What are transmitted by a wave? What are the transmitted by the wave? We are transmitting the energy, momentum, phase, but the particle are not. Means particle will produce a wave or particle will propagate and then transmit as a wave, and what are transmitting is the energy, momentum, and phase. Now waves, we define the types of waves according to their properties. First we discuss about the property which we take the direction of particle motion. We differentiate the waves. On the basis of the direction of particle motion particle direction, we define the types of wave into two parts. First is the transverse wave and second is the longitudinal waves. In the transverse wave, the motion of the particle is perpendicular to the direction of propagation in the wave itself, then it is a transverse wave. If the motion of the particle is parallel to the direction of propagation of the wave, then it is a longitudinal wave. Means we are defining the types of waves. First we are taking according to the direction of motion, in which we define the two type of waves. One is transverse wave, which is perpendicular to direction of propagation, and second is longitudinal wave, which is parallel to the direction of propagation of the wave. Now according to the number of dimensions, we define the waves into 1, 2 and 3 dimensions. In the 1D waves moving along the string or the spring, as we all notice in the daily life, then if a string is moved in a one dimension, then that type of waves we will get, and that is a one dimensional wave. Two-dimensional surface wave, or we can say it is a example is the ripple on the water. As we throw a stone in the water tank, then we see that there are the ripples on the water. The 3D waves, three-dimensional waves traveling radially outwards from a small source such as sound waves or light waves are the three-dimensional waves. Now these are type of waves on the basis of the dimensions. Now according to the periodicity, the waves are defined by the pulse wave or the periodic wave. The simplest periodic wave is the simple harmonic wave. We are talking about the periodic wave means a particular time interval, a wave which we are getting a particular time interval, that is a simple harmonic wave in which each particles undergo a simple harmonic motion. Those particles which undergo a simple harmonic motion is known as a simple harmonic wave. This is the example, this is the diagram of the simple periodic wave. Here we are having the x-axis in this direction and this is the y-axis. Here we are seeing that this is the type of periodic wave. There are the other kinds of periodic wave where we define the square wave. These are the square wave, these are the periodic waves, and triangular wave, these are the triangle waves. Modulated waves, these are the modulated wave. Here we define the modulated wave, which we will be getting the modulation and demodulation. This is a sawtooth wave. Here this the shape is as like a sawtooth. These are the different type of periodic waves. They are having after a particular interval. Now according to the shape of wave fronts, these waves are divided into the two parts. Number one is the wave surface and the wave front, and second is the ray, a line normal to the wave front indicating the direction of motion of the wave, or we can define it as a wave fronts are perpendicular to the direction of the ray. This we can explain by using the diagram. First we define there are two different type of wave fronts we will get. Number one is the plane waves and spherical waves. These wave fronts we are getting after the secondary waves generated from the primary waves. Now two different type of wave fronts, plane waves and the spherical waves. The plane waves where the wave fronts are in the form of planes and the rays are parallel straight lines. And in the spherical waves, the wave fronts are spherical and the rays are radial lines leaving the point of source in all the direction. This is the parallel straight lines and this is the radial lines leaving the point source in the all directions. It means we define the two type of wave fronts, plane wave and the spherical waves. Now here from the example we see here, this is a spherical wave and this is the plane wave. These are the parallel waves and these are the radially oriented. Here we see the rays are parallel and here the rays are radially oriented. And this is the surface which is in between the ray, this is the surface, and this is the lambda, which is distance between the two wave front, and this is the wave front 1, 2nd and 3rd in this manner. And here these are the wave fronts in the spherical form and this is the wave front in the parallel form. Now we see here that this is perpendicular to the rays. Here this is at an angle. This is also the rays. Here in the blue lines are the rays defined, and here these are the red line defined the wave front, and the surface in between that defined as the wave surface. The surface between the two different wave fronts are defined as the wave surface, and the distance between the two wave fronts is defined by the lambda. These are the spherical waves and these are the plane waves. Now waves in the different fields in the physics we define as the sound wave, water waves, earthquake waves, light waves, electromagnetic waves, which are very commonly used waves, gravitational waves, matter waves, lattice waves. These are the different type of waves we study in the physics. Now traveling waves, all the waves would travel or propagate. We are saying the propagation of the wave means we are talking about the traveling of the waves. Why here we are calling as a traveling waves? We are calling it as traveling wave as with respect to the standing waves or the stationary wave. Standing waves means there where we are not having any movement. Here traveling waves which are moving continuously. The definition of traveling waves, we would define it as the waves formed and traveling in an open medium system are known as the traveling waves. Here is the one simple harmonic transverse plane wave is an example. Now, in a mathematical expression, we define a one-dimensional simple harmonic transverse plane wave. Here, the vibration displacement defined by the y as a function of t is the time and x is the distance. We are defining a wave which is one-dimensional harmonic transverse plane wave, which is a travelling wave with the displacement y, which is a function of time and the distance. Now, here we see the difference between the vibration and the wave motion. We see here vibration defined as y, displacement with respect to time is known as the vibration, but the wave is defined as the time and distance. Here we are seeing that if the wave is vibrating, then we call it as a function of time. Y is the displacement, wave is displacing with the time t, that is the vibration. If we talk about the wave, then wave will having the displacement as a function of both time and distance. That is why we are writing as y as a function of x and t. This is the difference between the vibration and the wave motion. Now, here equation of a sine wave we define here. This is a simple wave. Here if we talk about, this is the x axis, this is the y axis, this is the lambda, this is the wavelength. We call it as a wavelength or distance between the two maximum amplitude. This is the maximum amplitude here one way, this is the maximum amplitude of the another. Then this at t is equal to 0, this is the initial time of the wave starts here, and here we see this is a simple sine wave. For this we write an equation x into t, x comma t. Here in place of t we are writing 0, because here t is equal to time period is equal to 0. Then this equation will be ym sine 2 pi by lambda into x, x defined by the distance and lambda is the wavelength, y is the amplitude. Here we see that now if t is equal to, this is a simple equation of the sine wave, as we are having this is the displacement, this is the amplitude ym sine 2 pi by lambda x. Now, here we see t is equal to t. Now, this wave is moving with the velocity v, then this lambda which was here will displaced with this value. This is nu t, and here we see this equation will change as t x t, which is equal to ym sine 2 pi by lambda x minus nu t. This is the nu t is the displacement from the with respect to the time. Here we see t is equal to 0, here t is equal to t. Now, this equation will change in this equation when the time period will change. Y x t is equal to ym sine 2 pi by lambda x minus nu t. Now, if there is initial phase constant phi in the sinusoidal wave, then the equation with respect to the time will become x minus nu t minus phi, because there is a change in the phase constant. That is why y x t is equal to ym sine 2 pi by lambda x minus nu t minus phi. Several important concepts about the waves like that. Number one, we define it as time period t of the wave is the time necessary for the point at a particular of x coordinate which undergo one complete cycle of the transverse motion. We are talking about the transverse, that is perpendicular to the propagation. During this time t, the wave travels a distance nu t. Here we define this is the distance at time t that must correspond to the one wavelength, that is the lambda. Now, the wavelength lambda is the length of complete wave shape. Here we see that this lambda is the one complete wave, shape of one complete wave. Now here we see that at if the time period t is equal to t by 4, then f is equal to 1 by t. Frequency of the wave defined f is equal to 1 by t, which is the inverse of the time period. At t, the wave number t, the t by 2, and third is this is a propagation constant, k is equal to 2 pi by lambda. These are the basic terms which we used in the wave. The frequency of the wave defined by f, which is the inverse of the time period. The propagation of the propagation constant, or we can say it as a wave number, which is 2 pi by lambda, which depend upon the lambda. Lambda is the one complete wave. Then angular frequency omega defined by the 2 pi by t is equal to 2, or we can write it as 2 pi f, that is a frequency. 1 by t is the frequency, and angular frequency can be defined in terms of frequency of the wave 2 pi f, or in terms of time period we define as 2 pi by lambda. Now this equation will become the previous equation, which is defined for the simple harmonic one dimensional wave y x t is equal to y m sin k x minus omega t minus phi, where we replace 2 pi by lambda with the k, x is already there, minus this 2 pi by t converted into omega t minus phi. As we see from the previous equation, then this we will get the new equation in terms of propagation constant, angular frequency. Now the equation of the sine wave travelling in the positive x direction will become y x t is equal to y m sin k x minus omega t minus phi. Here we see the previous equation, it is k x minus omega t minus phi. Now this equation for the plus x will be the same, k x minus omega t minus phi. This is the sine wave travelling along the x axis. If the sine wave travelling along the minus x direction in the opposite direction, then this term will become the positive, means y x t is equal to y m sine of k x plus omega t minus phi. This is the new equation we will get if we are the sine wave is moving in the minus x direction. Nu is equal to lambda f, then we can write it as omega by k, angular frequency divided by the propagation constant, that is defined the speed of the wave, means velocity of the wave defined by the lambda f, omega by k. Transverse velocity of the particle. How we calculate the transverse velocity? We know that the v is the speed of the wave transmitting. Then what is the velocity of the particle oscillating? That we will calculate what is the velocity of the particle. Now it is called the transverse velocity of a particle or for the transverse wave. The transverse velocity can be calculated as u y, as we are taking the y is the displacement for a wave which is dependent upon the x and t, is equal to del y by del t is equal to del by del t. Here we put the, this is the y from the previous equation, we will put here, which is y m sin k x minus omega t minus y m omega cos k x minus omega t. We take the differentiation of that equation, and then we are having minus y m, this sign converted into minus cos, and cos k x minus omega t, as we are taking with respect to the time period t. The transverse acceleration, we take the square of this velocity, it will be a y x t d square y by dt square, which is equal to minus y m omega square sin k x minus omega t, that we can write it as minus omega square y. This is the acceleration of the transverse wave. This is the velocity of the wave, transverse wave, and this is the acceleration of the transverse wave. Now phase constant for this wave, we define it as, in the equation we have y x t is equal to y m sin k x minus omega t minus phi. This k x minus omega t minus phi define the phase of the wave, and phi define the phase constant. Now we can write the two equivalent form of this equation, write it as yxt is equal to ym sin kx minus phi by k minus omega t, or we can write it as yxt is equal to ym sin kx minus omega t plus phi by omega. What we have done here, we are taking the omega constant here, and this will be the t, this t will be the positive if we take inside, that minus omega t plus phi by omega. This is the equation, wave equation for the phase constant phi. Now two waves, if you consider the wave A, which is having the phase constant minus phi, and another is not having a phase constant, that is defined by the wave B, means y is equal to ym sin kx minus omega t minus phi, y is equal to ym sin kx minus omega t, which is the wave B. Now here we see the wave A in the yx direction. Wave A is ahead of the wave B. This is the red color define the wave A, and the black is defined with wave B, and this wave A is ahead by the distance of phi by k. Here we see that the distance between these two is phi by k. Now yxt is equal to ym sin kx minus phi by k minus omega t. Now the equation for the wave A is defined as yxt is equal to ym k into minus phi by k minus omega t, and if this is related to the distance, this is related to the distance, this is related to the time. Now in case of yt, this is the displacement versus distance, this is the displacement versus time. The wave A is ahead of the wave B by the time phi by omega. This is the distance, this is the time. Now if it is by the phi by omega, then yxt, this equation will become ym sin kx minus omega t plus phi by omega. This is propagation constant and this is the angular frequency. Both the wave A defined as the distance or as the time period. Now we take an example here. If a transverse sinusoidal wave is generated at one end of long horizontal string by a bar that moves the end up and down, means this one string is moving in a form of sinusoidal wave, then end up and down through a distance of 1.30 centimeter. The motion is repeated regularly after the time interval of 125 times per second. Number A, we will calculate if the distance between the adjacent waves crest is 15.6, means highest peak we will get, then we will find the how we will calculate the amplitude, frequency, speed and the wavelength of the wave. Here we see the amplitude can be find out, ym is equal to 1.30 divided by 2, because amplitude is 1.3 knot. This is the distance, this is the this define the 1.30 centimeters define the distance. Here we are finding the amplitude will be the half of this, that is 1.30 by 2 centimeter, which will be 0.65 centimeter. The frequency, here we are having the 125 times per second, this define the frequency, and wavelength defined by the distance between the adjacent wave crest, that is lambda, is defined by the 15.6 centimeter. Then speed we can define, nu is equal to lambda f, which is equal to, we will multiply these two by 19, this will be 19.5 meter per second. The second part is assuming the wave moves in the plus direction, plus x direction, t is equal to 0. The element of the string at x is equal to 0 is as its equilibrium position, y is equal to 0 and moving downward. Then the equation of the wave can be written as yxt is equal to ym sin kx minus omega t minus phi. As we know, that is defined as for the t is equal to 0. Now imposing the given initial condition y is equal to 0, del y del t less than 0, x is equal to 0 and t is equal to 0 yields y m sin minus phi is equal to 0 minus y omega cos phi less than 0. Here we take y, here we take this value, then phi is equal to 0, y x t is equal to y m sin k x minus omega t. We will put all the values here, then we will calculate the wave equation from this. Thank you.
With this note, thank you and thank you so much for giving us this session on wave motion. Dear friends, there is a lot more for you. You are requested to be with us as we are going to be available for you after a short break, and we are going to give you more and more of knowledge on wave motion. Thank you for watching us. Hello friends, welcome back to this session. Friends, as you know that today we are talking on wave motion in detail and we are giving you the basics of wave motion. For the discussion we have with us in our studios Dr. Sonia Bansal. Dr. Sonia Bansal is assistant professor and she is teaching in YMCA University of Science and Technology. Friends, if you have any question pertaining to today's lecture, then feel free to talk to us through toll-free number. The toll-free number is 1800110430. Now I would like to welcome our guest Dr. Sonia Bansal once again. Hello.
Thank you, Geetika. Okay, dear student, now we discuss the second problem, which is used to calculate the frequency and acceleration. Now, from the expression, we have the velocity and acceleration of the particle p at xp is equal to 0.245 meter. Now, we evaluate the y. Y is the displacement, uy is the velocity of the wave, ay is the acceleration of this particle at time period t is equal to 15.0 millisecond. Now, we know that uy, as we already solved, xp, p for the particle p into t is defined as y minus ym omega cos kx minus omega t. Now, acceleration will be defined as ay xp, which is the function of displacement and the time, minus omega square y. B is equal to, now for to calculate the displacement, we have y is equal to minus 0.61 centimeter we calculate, and uy is equal to 173 centimeter per second. Here we put all the values in this equation, and again the acceleration will be 3.8 into 10⁵ centimeter per second square. After solving this, we will get the result. Now, we discuss about the velocity. Velocity plays a very important part in the wave motion. Wave velocity means we are talking about the speed. the wave velocity defined by the two velocities. First is the phase velocity and second is the group velocity, and both are related to each other. We define it as here. First we discuss about the phase velocity. What is a phase velocity? It is for the monochromatic wave, the velocity of the motion of certain phase in a wave. The velocity of motion of certain phase in a wave that we define by the velocity v is equal to omega by k. What is omega? Omega is the source of the wave and mu is the medium, and then this is for the non-dispersive medium. The wave speed on a stretching string is the phase velocity. Now here we see the dimension analysis with nu is equal directly proportional to f by nu, and here from the mechanical analysis nu is equal to root of f by nu. Now here we see this is the wave velocity which is defined by the nu. We can say it is a v. Now f, this is the force and this is the force, this is the angle and this is the distance. Here we are talking about a string is moving. The force working on the string is defined as f net into f net x is equal to 0. F net, force net is for the y axis, this is for the x axis is equal to 0, this is for the y axis, this is will be 2f sine theta, or we can write it as 2f theta, which is equal to f del L by r. And here from here we can calculate that wave velocity is equal to dependent upon the force as well as the refractive index, which is or define it as the F is equal to tension force exerted between the neighboring element, and this nu is the mass density, which is the mass per unit length. This define the wave velocity. This nu is defined as the mass density, and we define dependent upon the tension force or the force exerted between the neighboring element and the mass density of the particle. Now when a wave passes from the one medium to another medium, the frequency will be the same, and we define it as the f1 is equal to f2. Lambda and velocity may vary, frequency and the distance between the two amplitude will vary. Group velocity, where we define the all the velocity in a group or group of waves defined by the velocity. For a group of waves with different angular frequency, if we talk about non-dispersive medium, then all the waves with different omega moves with the same speed. When the waves are having the different angular frequency, they will move with the same speed, which is v, determined by the medium. If we talk about the non-dispersive medium, this here we define this is the x-axis, this is the time is equal to 0, and we see here at time t, and when it is moving with the velocity v, at time t the wave will be the same, the shape will be the same. It means it is moving with the same speed v, and this is the wave in the non-dispersive medium. In the dispersive medium, different frequency, different speeds. Here we see the shape of wave is changing as the time is changing. The shape does not keep same. This is the difference between the non-dispersive medium and the dispersive medium. In the non-dispersive medium, different frequency, same speed of the wave. Here we see in the example, time period is equal to 0, time period t moving with the velocity v, this shape is same after the time interval t. But here for the dispersive medium, all the waves are having a different frequency, different speeds, shape is changing at time t. The group speed is needed to describe the wave, which is defined by the v is equal to d omega by dk. Omega is the frequency, angular frequency, and k is the propagation constant. The group velocity defined v is equal to d omega by dk. All the mediums met is assumed to be non-dispersive. The next is the wave equation that will define the energy in a wave motion. How the energy will define in a wave motion? Here energy in a wave motion as shown in this figure, this is the distance, this is defined by the this is dx and this dl and dy. Now here we see the waves, one wave A and second wave is B. At this time period for the one wave is T1 and time period is T2. These are moving along the x-axis. Now here uy is the speed, uy is the speed. Now from this diagram we see that the waves travelling along the string at time T1 and T2. At time T by 4 later we will see that how we calculate the rate at which the kinetic energy is transporting and the rate at which the potential energy is transporting. Kinetic energy and potential energy we will calculate for both the cases as it is moving with the velocity with the velocity uy. Now here we see that dk by dt define the rate of change of kinetic energy is transporting by the wave. This is the rate at which the potential energy is transported. First we take dk by dt potential kinetic energy. dk is defined by the 1 by 2 dm into uv. This is a simple propagation equation. Now here we put the value of uy and this dm defined by the u dx, nu dx and minus y, this define the velocity. Now this equation will be 1 by 2 y m square omega square nu dx cos square kx minus omega t. dk by dt we take the differentiation with respect to the dt which is equal to 1 by 2 mu omega square y m square dx by dt cos square kx minus omega t. Now this equation will become dk by dt is equal to 1 by 2 mu omega square y m square nu v cos square kx minus omega t. This is the propagation constant. Now for the du by dt for the potential energy, this value for the kinetic energy, and now we calculate for the du. Du we define as f dl minus dx. Dl is equal to root of dx square plus dy square, that we have taken from this side. This from here we taking the d square, dl square is equal to dx square plus में dy square. This will be du is equal to f into, we put the value of dl minus dx. This will become f dx, we take the dx common, 1 plus dy dx square minus 1. The quantity dy dx is the slope of the string, and if the amplitude of the wave is not too large, this slope is very small, so we can write it as 1 plus z1 by 2, approximately 1 plus 1 by 2 z. Now we can replace this value by du f dx 1 plus 1 by 2 dy by dx square minus 1 and so on. After solving this, we will put dx by dt is equal to v, mu is equal and this value will be, this v will be replaced by omega by k square. Velocity, this define the phase velocity, omega by k square mu dx by dt will replace by the v. dy by dx will be written as this form. The finally we will calculate the du by dt which is equal to dk by dt 1 by 2 mu omega square y m square v cos square kx minus omega t. As we see from this expression that this potential energy is equal to the kinetic energy. This dut by dk by dt is equal for the propagation of the wave. We have dk is equal to du is equal to 1 by 2 mu omega square y m square dx cos square kx minus omega t. Now here from this equation we can note that dk and du are both 0. when the element has the maximum displacement, means element at the relaxed length, both the value, the energy will be the 0. The mechanical energy dE, which is equal to du plus dk, kinetic energy plus the potential energy, is not constant because the mass element is not the isolated system. The neighboring mass elements are doing work on it to change its energy. So, this value will never become a 0. Both are 0, but here we see in the mechanical energy is not the constant value. And next is the power. Power we can define it as the rate at which the mechanical energy is transmitted. That define the power, which we can define it as P is equal to dE by dt, energy with respect to the time, is equal to dE is equal to du plus dk, or we can say, we can write it as 2 dk because du is equal to dk. So, we can take 2 times of kinetic energy. Now, P is equal to dE by dt. Now, from the previous equation we can write it as here, we will put the value of dk here. The average power defined by the P average is equal to 1 by 2, 0 to full time period, we are taking it as dE by dt d is equal to 1 by 2 mu omega square ym square v. Intensity, which is the P average divided by the amplitude. Now, the spherical wave defined by the it as a is the area, PAV divided by A. Now, for the spherical wave, intensity will define by power by the area, which is 4 pi r square, directly proportional to the radius of a circle, and then we can define it as ym displacement directly proportional to the 1 by r, as we know that the intensity is the square of the amplitude. That is why here we write it as ym directly proportional to 1 by r. Now, what is the principle of superposition? In case of the principle of superposition, the 2 or more waves travels simultaneously through the same region of the space. That is known as the superposition of the wave, and that principle is known as the superposition, means 2 or more waves are moving simultaneously. That is known as the superposition. Now, here we define the 2 waves y1 and y2, they are moving simultaneously with the same displacement and with the same time period. The total amplitude or total displacement we define by the yxt is equal to y1 xt plus y2 xt and so on. The interference of the wave, in the interference of the wave, when the 2 or more waves combines at a particular point or they follow the superposition principle, then waves are known as the interference wave. The phenomena is called the interference. When the 2 waves are interfere each other or the superimpose each other, that phenomena is known as the interference. We consider general case of equation. Here we see for the one wave, which are one wave y1 having the displacement y1 xt related to the displacement and time, which is equal to ym sin kx minus omega t minus phi 1. We know that kx is the displacement, x is the displacement, x is the propagation constant, omega is the frequency, t is the time period, and phi 1 is the phase constant for the one wave. For the second wave, y2 is equal to xt is equal to ym sin kx minus omega t minus phi 2. Here we see that this amplitude is same, propagation is same, frequency is same, but this phase constant is different for the 2 waves which are going to be interfere. If we take the resultant amplitude, which is equal to yxt is equal to y1 xt plus y2 xt. Ym is equal to sin kx minus omega t minus phi. We will put these values in this equation. Now, after solving this, we will get 2ym cos del phi by 2 sin kx minus omega t minus phi. Now, where we can write it as phi dash is equal to phi 2 plus phi 1 divided by 2, or del phi can be written as phi 2 minus phi 1. Then the resultant wave corresponding to the new wave having the same frequency, but with the amplitude defined by the 2ym cos del phi by 2. If the phase if they are in a phase, means del phi is equal to 0. There is no change in the phase. The resultant amplitude will be 2ym. This is known as the constructive interference. When if the two waves are in a phase, means there is no change in the phase difference, delta phi is equal to 0, the value will be the maximum, and we can say it is a constructive interference. If del phi is equal to 180, it will be the out of phase, the resultant amplitude nearly 0, and then this will define the destructive interference, means intensity will be minimum in that case, but here in this case the intensity will be the maximum. Here the two waves are interfere constructively, the two waves interfere destructively with giving to the minimum energy, here giving the maximum energy. Here we get the bright point, here we get the dark point. Resultant amplitude we will define by this is wave 1, this is wave 2, and we take the resultant amplitude, it will be y1 plus y2 if they are in a phase. If they are in not a phase, then you see that this is amplitude is maximum in this case. Here the amplitude is minimum in this case when del phi is equal to 180 degree. Now this is the diagram which define the interference of wave. Here the wave are coming from the source, and here we are having the spherical wavefront is passing from the two slits S1 and S2. Now at the photographic plate, or we can say on the screen, this process is taking place as superposition. Here the two waves are superimposed to each other. When the waves are in phase, then they will give the constructive interference. Here at the center we are getting the bright point because the waves are constructively interfere, and here we are getting the dark point, here the waves are destructively interfere. When the wave from the wave source reaches the two slits, it becomes a wave with the same frequency, parallel vibration directions, the same phase or a constant phase difference, and the wave interference phenomena occurs on the screen as we see, showing the bright and dark points. When they are constructively interfere, then we get the bright point. When they are destructively interfere, we get the dark point. So simultaneously we are getting the dark and bright point on the screen. This we can define by the Young's double slit experiment, which is the interference experiment also. This is one of the best experiment, and it is ranked 5 in the top 10 beautiful experiment of the physics. Here we see that the Thomas Young's defined the Young's double slit experiment. Similarly here he used the sunlight, and this sunlight passed from the single slit. This is the screen of the single slit, and it is passed from here, then a diffracted coherent spherical wavefront. He got it after passing from the single slit, the sunlight he used. After that, this is the screen of with having the two slits, and this the coherent spherical wavefront again passed from these two slits. Now here the line of waves out of the step sum, which gives the destructive interference, and here the line of waves which in the shape give the constructive interference. The red line define the brighter point and the black line define the darker point. This is the dark fringe, A is the bright fringe, dark fringe, bright fringe, and in this manner we are getting the interference pattern. This was the Young's double slit experiment. Now the two-dimensional simple harmonic propagation in the same direction, their frequency and the amplitude A will be the same. If the phase are opposite, then the amplitude after the superposition will be the 0. That's why we are getting the constructive and destructive interference. Where is the energy of the wave gone? Then the phases are the same, the amplitude after superposition we are getting the maximum amplitude, that will be the 2A. When the other parameters are same, the energy of the wave is proportional to the square of the amplitude, and the energy of two waves before the superposition is A2 plus A2. After that it becomes 2 times after superposition. How is the energy will come out more? the most amount of energy can be created, not be destroyed. So maximum intensity we will get the interference. Now next is the standing waves. What are the standing waves? We consider the effect of superposing the two component wave, equal amplitude and the frequency, moving in the same direction in the string. Then what the effect of the wave moving along the string in the opposite direction? Then what happened? We represent the two waves as y1 is equal to ym sin kx minus omega t, and the second wave is the ym sin kx plus omega t, having the equal amplitude and frequency. This is the amplitude and this is the frequency, moving in the same direction of a string that we already discussed. Now if it is in the opposite direction, then what happened? Then this will be the minus, this minus for the negative direction. Now it is moving in the opposite direction. Now this equation will become the resultant wave y is equal to y1 plus y2 ym sin kx minus omega t plus ym sin kx plus omega t. The resultant amplitude defined as y is equal to 2ym sin kx cos omega t. Now from this equation we define the standing wave. It is not a travelling wave because x and t do not appear in the combination. Here we see x minus Vt or x plus Vt required for the travelling of the wave. So this wave is known as the standing wave, and the standing waves have nodes and antinodes. In the standing wave, amplitude is not the same for different particle. The wave here is different from that of the travelling wave. Then we define it as a node or antinode. How we define the node? First we define the node where the position amplitude having the minimum value of 0, where the amplitude will be the 0. Antinode, the position where the amplitude has the maximum value, and nodes where it is amplitude having the minimum value. So 2ym sin kx is equal to 2ym. We can put this value, kx is equal to n plus 1 by 2 pi, n is equal to 0, 1, 2. Then we define x will be the n plus 1 by 2 lambda by 2. At these points x is equal to lambda by 4, 3 lambda by 4, 5 lambda by 4 and so on, we are getting the antinodes points. At x is equal to 0, lambda by 2, lambda, 3 lambda by 2, 2 lambda and so on, we get the nodes where the minimum amplitude, because here the maximum value of the amplitude defined by the 2ym, here the minimum value of the amplitude defined by the 0. This is the example of the wave. Here we see that 2 from the standing wave, this is the forward wave which is defined in the black color. This is the backward wave which is defined in the blue color, and this is the resultant wave of the forward and the backward wave at the different values of t is equal to 0, t is equal to 1 by 8 t. Here we see the different values, and the different values of x we are getting the nodes, and these are the nodes, this is the antinodes we are getting. The energy of the standing waves, how we will define it as, for the standing waves the energy cannot be transported along it because the energy cannot flow past the nodes which are permanently at rest. So this is the UK potential energy, this is the kinetic energy, potential energy, kinetic energy, potential kinetic energy. As it is not moving, so the energy will not get it. Thank you.
With this note, thank you so much for giving us this session on wave motion. Dear friends, you are requested to write to us at info.cec@nic.in if you have any query or if you wish to give your feedback. We are taking your leave with the promise that we are going to meet again soon. Till then, take care. Goodbye. Thank you.
Thank you
once again.